We begin by defining the physical parameters of the environment, a region of space occupied by an external electric field. In a uniform electric field, the field strength vector E remains constant in both magnitude and direction across every point in the system. We introduce an electric dipole into this field, two equal and opposite charges, positive Q and negative Q, oriented at an arbitrary angle theta. The field exerts forces on these charges in opposite directions, a vector of QE on the positive charge and negative QE on the negative charge. These forces are equal in magnitude, but perfectly opposed, resulting in a net translational force of 0. This ensures the dipole's center of mass remains stationary. While the center of mass is fixed, the forces act along different lines of action. This offset configuration inherently shifts the physical behavior of the entire system into the domain of rotational mechanics. The rotation is quantified as torque, defined as the sum of the cross products of the position and force vectors for each individual charge. The first line of the derivation establishes total torque as the combined rotational influence at points A and B. Vectors OB and OA define their positions relative to the origin. Substituting the electrostatic force equations yields a cross product with the uniform field strength. This creates a complex vector sum that depends on the arbitrary placement of the origin. To derive a universal formula, we must simplify this relationship through geometric manipulation. Direct your attention to the negative sign inherent in the force acting on charge A at position OA. Algebraic properties of the cross product allow a negative scalar to be moved between the two vectors in the operation. Moving this negative sign from the charge to the position vector transforms the term into negative OA cross QE. Reversing a vector's direction in space is the geometric equivalent of applying a negative scalar, turning vector OA into vector AO. This spatial reversal reflects in the third line of the derivation, using the positive term AO cross QE. Both terms now share a common vector factor of QE. Factoring this out isolates the addition of the position vectors inside the parentheses. This manipulation shifts the focus from the individual charges to the internal geometry of the dipole structure itself. We are left to resolve the geometric sum of the two position vectors, AO plus OB. Using tip-to-tail addition within the coordinate system, we can trace the path from point A to O, and then from O to B. The result of this addition is a single displacement vector, AB, which spans the total distance from the negative charge to the positive charge. Substituting this result back into the derivation gives us a simplified expression. Torque equals Q times the displacement vector AB cross the electric field E. We define a new vector quantity, P, as the product of charge magnitude and displacement vector AB. This property is the electric dipole moment. The final derivation provides the vector relationship, P cross E, and the scalar magnitude PE sine theta. The torque on any dipole is determined by the cross product of its inherent moment and the external field strength. Mechanical equilibrium occurs at the specific orientations where the magnitude of the torque drops to 0. Solving the scalar equation for a torque of 0 requires identifying the angles where the sine of theta is 0. This occurs at two distinct solutions, 0 degrees and 180 degrees. At 0 degrees, the dipole moment aligns perfectly with the direction of the electric field. At 180 degrees, the dipole moment is anti-aligned, pointing directly opposite to the field. While both states result in 0 torque, their physical stability is determined by how the forces respond to a change in orientation. We can test this stability by introducing a small rotational perturbation, a slight nudge away from the equilibrium angle. If the aligned dipole is nudged, the resulting force vectors generate a restoring torque that returns the system to its original alignment. Because the system corrects for the perturbation, 0 degrees is a stable equilibrium. If the anti-aligned dipole is nudged, those same forces generate a torque that pushes the dipole further away from its equilibrium point. Since the system amplifies the perturbation, 180 degrees is an unstable equilibrium. This vector relationship governs the magnitude of the rotational force and determines the overall structural stability of the entire dipole system.